And right, so today's keynote speaker, we're very happy to have Bryan Parno. So, taken from his bio, Bryan is a professor of electrical and computer engineering at CS department at Carnegie Mellon University. If you check out his website, he has a very long list of news with a lot of awards, which I'm not going to read all of them because it's going to take longer than 4 minutes, but that just goes to testify how influential his work has been. And just to summarize briefly, his research primarily focuses on investigating long-term fundamental improvements in how to design and build secure systems. As a result, his work combines theory and practice to provide formal, rigorous security guarantees about concrete systems with an emphasis on creating solid foundations for practical solutions. And Bryan, the floor is yours. Thanks again for accepting to give us the keynote here.
Cool, and thank you very much for that kind introduction and for having me here today. Without further ado, I'd like to start by talking about cryptographic protocols and the way in which we find them all around us. It would be hard-pressed to find an application today that you are using in any possibly security-sensitive session that does not involve a cryptographic protocol somewhere under the covers. And that would be fine, except for the fact that these protocols are horribly complex. So when you think about something like TLS, right, TLS is complicated, but it also depends on the X509 standard for certificates to figure out who you're talking to. It depends on all the fancy crypto that's going on underneath. And it depends on sort of low-level, boring stuff like parsing and serializing that is nonetheless critical for security and correctness. And when I say complex, I mean both in the textual sense. So if you look at the text for the RFC specifying TLS, it's over 100 pages of English. And as you might imagine, that leaves a lot to be desired when it comes to formal definitions. If you look at the code for something like OpenSSL, they have over 60,000 lines of code just for the protocol logic, and over 300,000 lines of assembly and C code implementing the crypto. But don't worry, some folks came along and said, we're going to make a boring version of this. We'll take out all that stuff we don't need and make it really small and simple. And there's probably still some work to be done there. And as a result of all this complexity, it's not too surprising that over time we've seen problems in every single one of these components. And those problems show up in all the major implementations. It doesn't seem to be plateauing. We still see them coming out pretty regularly. And it's everything from low-level buffer overflows like the freak attack, or the Heartbleed, to problems with the protocols themselves. So even if you accurately implemented the protocol itself had a problem. And so, of course, our goals are to try and come up with verified replacements for each one of these components, and then ideally prove that together they all give you that high-level abstraction that you want from the protocol, in this case, a secure channel. Along the way, we'd like to also make sure that we get widespread deployment. So it's hopefully a one-line command, and all of a sudden you're running our verified crypto. And a key part to making this happen is to make sure that you can interoperate with existing code, because we don't want to actually go off and re-verify all of Chrome. That's going to be somebody else's PhD thesis. And it means getting performance right. Because historically, the world has, when given a choice between performance and anything else, they choose performance. And so that's one of the reasons why we focus heavily on that. The other part is that we want to, along the way, improve the tools and make them better and more usable so that it's not just a verified artifact that emerges at the end, but a methodology and a set of reusable tools that other people can go off and do this too. And you may have heard of the Z3 SMT solver and the lean theorem prover. One other tool you'll hear a lot about in this talk is the Veris tool, which is something, it's a large collaboration we're working on to verify Rust code. All right, so in this talk, I'd like to cover all the components of this stack. But in the interest of time, I'm only going to touch on most of them very briefly. And then I'll focus on the high-level story behind protocols, because that has the most intense compilation. And that seemed appropriate for this audience. All right, so starting at the very bottom, you do somehow have to get the bytes coming off the wire into a format that you can work with. And so we've developed a tool called VEST for automatically generating verified parsers and serializers, inspired in part by prior work like Everparse. And so our goal is to be able to take binary data formats, ones where somebody has already specified what it's supposed to look like. We don't have any freedom in how to arrange it. And we want to be able to describe these in a very simple, expressive way, allow people to extend the format to accommodate the fact that some of these protocols are really gnarly. And of course, we want it to be fast to execute. But we also want it to be fast to verify, because if you're sitting there working on your format, trying to make sure you got it right, you want to get quick feedback. And finally, of course, I'm a security person, so we need it to be secure in the sense that there should be no ambiguity when you're parsing or serializing the data. And these days, we also need to care about side channel freedom, so we're not leaking stuff through timing or memory accesses. So how do we do this? Right now, you take your high-level format that's specified informally, you write it down in a formal definition that has actual semantics to go along with it, and out pops a series of definitions of high-level structures in your Rust code, has concrete serializers and parsers that will execute efficiently, and it comes with specifications of their correctness and security. And this is all built on top of a library of combinators that we've already sort of manually verified to have all these nice properties and to compose in a clean, natural way. And then we run this through Verus. Hopefully, in all of the formats we've tried, you, in a few seconds, get a verification result telling you that all these nice properties hold. And then out the other side, you can integrate it easily into existing Rust projects, either ideally verified or, if we have to compromise, we'll say unverified Rust code as well. All right, so this is the high-level view. The key ideas that came away from this was that we're actually able to automatically and generically provide side channel resistance, which is not something that other parser work has looked at. We've also found that we get a lot of mileage out of the trait-based system in Rust, which, if you're not familiar with it, is a little bit like Java interfaces, a little bit like type classes. And by specifying our combinators using these traits, we get very nice composition. It's very natural to express the composition of two traits and two objects with the same trait. Extensibility is easy because there's a very clear defined interface. And we get good verification performance because we're able to avoid some of the complications that come of trying to deeply encode higher order functions in an SMT-based proof assistant. In addition, we've done a bunch of case studies. We've got the TLS 1.3 format, message format, Bitcoin transactions, WASM, I think the first fully verified parser for WASM. And as a result, we're able to get very strong performance. The combination of clever encoding and the fact that we're using Rust means that we can actually, in some cases, beat. So we're like 2 times faster than Bitcoin's own parser. And we get several orders of magnitude on the verification performance. So sadly, I can't spend more time on this. Instead, I'd like to talk briefly about Evercrypt, which is a project that came out of the Everest project that I, and along with some other folks at MSR, founded almost 10 years ago. And here we wanted to have a cryptographic provider. And these days, what a cryptographic provider means, it's not just a list of cryptographic algorithms, though that's nice. We also want it to be usable in the sense that it's easy to plug into existing code. So that means interfacing with C or assembly. And to automatically pick the best implementation for your platform. To say, oh, I see you have the latest version of the vector instructions on Intel. We can do something custom for that. Oh, you're on ARM. We can do something on using Neon. Or none of the above. We'll fall back to a generic C implementation. And finally, best practices in crypto these days is to have an agile implementation. So instead of hard coding SHA-1 into your application code, you want to instead say, I have a hash interface, and make everything parametric on just the one place where you instantiate the hash function. So that way, when SHA-1 gets broken, like it was, it's sort of a one-line change to move to a more secure format. This is becoming increasingly important as we see more work going on the cryptanalytic side, and as the specter of quantum computers start to loom. So the nice thing is we were able to do all this in Evercrypt without giving up on performance. So we are comprehensive in the sense that basically any sort of cryptographic primitive you want, we have everything from low-level ciphers to high-level public key and sort of simple APIs like box and unbox that were popularized by the NACL cryptographic library. And we can do all this without compromising on performance. So to illustrate that, this is one table from when we published this work. The green ones are verified, the red ones are unverified. And you can see there's different performance based on whether it's portable or not. But the important thing is that at the time, we had the fastest implementation in the world. That wasn't because we were crazy optimizing the crypto. Instead, we took an existing academics group's work, taking advantage of some of the latest Intel instructions. And they'd actually developed it and handed it to Mozilla and said, hey, we noticed that Firefox is using this really slow implementation. Wouldn't you like to use this fast one? And Mozilla said, yes, we want our browser to go faster. They ran it through the regression suite and found out in some cases it would compute the wrong value for the elliptic curve. This is obviously concerning, and they said, hey, this is a big problem. The academics said, okay, no, just a minor problem, we'll fix it. They carried the one in the right place. and handed it back. Mozilla tested it again, and once again, it came up with the wrong answer. At that point, Mozilla said, we'd rather have something that's slow, just go away, academics, stop bothering us. So we took that implementation, we fixed it, added some optimizations, and then proved that those optimizations were actually computing the whole thing correctly. And after a bunch of work, we managed to get it adopted by Firefox. So I think this is an interesting case where verification is not just telling you what you already have is OK. It's saying, hey, we can make it safe to try something more adventuresome, possibly get you more performance than you could otherwise. All right, so once you have crypto, you can start verifying cryptographic certificates. So these are certificates that tell you, who does this public key belong to? Is it actually Amazon you're talking to, or is it somebody impersonating Amazon? This is a challenging space to verify, in part because there is no good specification. So for verification, you need to have a spec. The specification for validation is described across 4 or 5 different mutually, sometimes conflicting and often ambiguous RFCs. And many of the features they specify are optional. So you may choose to do this, or you may choose not to. There's also certain TLS clients, like browsers, have an elevated standard. So they have a whole list of 100 or plus more requirements they have to adhere to. Something like OpenSSL doesn't. On top of that, individual implementers, like Firefox and Chrome, deliberately violate these standards for either backwards compatibility or security concerns. So even if you could somehow magically encode all these RFCs mathematically, the thing that you verified would not be of any use to Firefox or Chrome because they don't want to follow that standard. And they don't want to follow it in different ways. They don't even agree on how they don't want to follow it. The other problem, of course, is that we want to get a strong security guarantee, but we also want performance because, see above, read performance. So our solution to this is actually to come up with, to generically verify the validator with respect to a user-defined policy. So the idea is that you can very succinctly describe how you want to validate certificates, and we provably implement that policy for you. And that way, Chrome can make their decisions, Firefox can make their decisions, and they both wind up with a verified implementation. And to get good performance, we heavily use DSLs, both for the policy language and for the parsers that we wind up generating. So just to very quickly give an overview. So when you're validating a certificate chain, you're actually testing a claim. Like, I'm connecting to Amazon, and the current time is this really Amazon? You have some evidence that the server provides or that you've collected from the web of other certificates. And baked into your browser or your OS, there is a store of root certificates that says, yes, these are trusted entities. So internally, what we do is we first parse all of these certificates, and then we pass them off to a path builder. So the idea here is you have to find a path of linked certificates that go from the leaf for the server all the way back up to one of the root certificates. And to do that, you have to check cryptographic signatures. And for that, we use the Evercrypt library. Once you have a bunch of candidate paths, then you apply the policy. And the policy is informed by the user-specified policy in our domain-specific language, which we then automatically compile to verified Rust code that implements that policy. And so we can check the paths and ultimately wind up with a decision that, yes, this is really Amazon, or no, it's not. And the nice thing is this all comes with an end-to-end specification telling you that if we say it's a valid certificate, it really is valid. And if we say it's not, then we have a good reason for it. So some lessons we learned along the way is that we're actually able to get real-world expressivity with our domain-specific language. We coded up Firefox, Chrome, OpenSSL policies, the ones that they actually implement, and compared them on 10 million some certificates from the wild. And they agree, except in places where there are bugs. So we found a couple of interesting bugs along the way. And we also found that we were able to get strong performance. So we could meet or beat all the existing implementations for the real-world ones. There's been some prior work on doing parts of this, but we're 2 to 3 orders of magnitude faster in execution time and use 3 orders of magnitude less memory. So we're taking a big step towards practicality there. All right. So that's all the infrastructure we need to even begin to talk about verifying protocols. And for that, we're going to use a tool called OWL that we've been developing. And before I tell you more about it, let's just talk about why this is a hard problem to begin with. So when we first set out on this project, I had no intention of verifying protocols. I wanted to pick up an existing tool like Tamarin or ProVerif and just turn the crank and focus on the other parts and the parts above the protocol. But as we started looking at the literature, we realized that none of the tools out there actually satisfied all 3 of these criteria at the same time. So the first one that you want is something called computational security. Right? So this is the gold standard, what a cryptographer would do if they were actually writing out a proof by hand, but often they can't be bothered to do something as big and complex as the kinds of protocols we're looking at. This is in contrast with symbolic security, which many existing protocol verifiers do, where you use an abstract sort of term algebra, and you have rules that say, if the adversary knows this and this, then they're allowed to learn something else. This is very convenient because it's easy to automate. Right? You can sort of do a bunch of term rewriting, and it's easier to build automation for that. But the contrast is with computational security, where we say everything's operating over generic bit strings, and the adversary is an arbitrary polynomial time algorithm that we have no insight into. It can just sit there and do anything it wants, except violate cryptographic assumptions. For example, that AES is a secure encryption scheme. And historically, the difference between these two is you get better automation here, but you get weaker security guarantees. So it rules out some kinds of attacks, but it doesn't, because of the abstraction, you lose details for things like attacks that exploit the fact that messages are actually finite length bit strings, or that you have to split them up into smaller pieces to send them on the network. Whereas if you can get computational security, then you get sort of what the best that the crypto world can offer us. The other piece that we want is proof modularity. Right? This is something that we kind of expect from our code verifiers, and we'd like that from protocols as well. And this also reflects the reality that complex protocols these days, like TLS, can actually be broken into pieces. So there's the handshake where you agree on which keys to use, there's key negotiation, and then there's actual secure transport across the wire. And ideally, we prove each one of these secure individually, and then show that that implies that the composition, namely TLS, is itself secure. This is actually one of the major challenges here, because secrecy and integrity properties don't compose nicely. Traditionally, they don't compose as nicely as correctness does across these boundaries. And finally, partly because developers are lazy, and partly because these protocols are really large and complex, we want good proof automation. So we saw before that the English descriptor, or the code for this can be 60,000 lines or more. The cryptographic operations are very complex. This is not just textbook RSA. There's many different steps where you're computing something, you're computing a hash, you're combining that hash with a bunch of other stuff, deriving keys, and then using those keys for various purposes. And at the same time, you're often keeping track of a complex state machine to decide, oh, what state am I in, what kind of messages do I expect, and what should I do when I'm in that state. So trying to do all this by hand is going to be horribly tedious, so we really want strong proof automation to help us. All right, so basically we have these three properties, and if you look around, many of the existing tools satisfied one or two of them, but unfortunately we didn't have any satisfying all three, so we said, all right, damn it, we're going to have to write our own tool here. All right, and that's where we got OWL, which you specify a high-level description of your protocol, you feed it in, and out the other side you get a secure, fast, interoperable implementation. And it provides all three of the nice guarantees of security, modularity, and proof automation, which means that we have this nice framework where you can actually build protocols in a sort of logical, compositional way. You can take pieces from other protocols and staple them on with new pieces, which is kind of what happened with the Quick protocol. And you can actually make that work in a proof framework. So internal to OWL, we take this protocol description, we run it through a slightly fancy type checker, and we have this guarantee from the type system that if it type checks, then it's computationally secure. So there exists a series of computational proof steps that would show you the same thing that a cryptographer would show you. Assuming it checks out, we then have a compiler that does sort of security-preserving compilation to give us an implementation that's safe, correct, and that doesn't leak anything more than the original functional description that you gave us. So that's the high-level overview. And the one important thing to point out here is it's all automated, modulo getting the types right when you feed it in at the beginning. So the type checking happens automatically, the compilation happens automatically, and the implementation gets verified fully automatically. So the rest of the talk will be going into more details, starting with the type checker. So to sort of give you a little bit more concrete idea of what kind of protocols we have in mind, here we have a server and a client that want to talk to each other. And in particular, they want to get some important message X from the client to the server. To do that, we're going to assume they both have a pre-shared key, your PSK, and they're going to use that to secure the messages they send. And they're going to do it over a completely insecure network, meaning an adversary can drop, manipulate, inject, and rearrange any packets that go by. So the server is going to generate a fresh key k, and it's going to use that to encrypt. It's going to encrypt that with the pre-shared key. The client on the other side is going to use the pre-shared key to decrypt that and obtain the k sub x. And then we're going to use k sub x to encrypt x and send it to the server. Because the server has k sub x, they can obtain x. Hopefully nothing too surprising here. But yeah. OK. So what are our security goals? Right? So it's sort of twofold. We want integrity, meaning that if the server receives a value, it really is the same x that the client sent. And security means that all of our secrets, the pre-shared key, x, and the k sub x, remain secret unless one of the parties is corrupted. Right? Obviously, if the adversary compromises the client, then some of these guarantees fall down. All right, so how do we encode this in OWL? Right, so we first start off by naming all of the secrets that we're going to keep track of. And you can see that we distinguish between x, which is a nonce, basically, from our perspective, a random value, and things that are going to behave like keys. And when you define an encryption key, you also specify what kinds of things is it allowed to encrypt. So you could say it's allowed to encrypt even values, or in this case, we say k sub x is only allowed to encrypt x. So that's where our integrity guarantee is going to come from. And then we write down a description of what the different parties are going to do in a hopefully fairly readable functional style. Right? So in this case, the client is going to read in an input. It's going to attempt to decrypt it. If the decryption succeeds and gets some value, it's going to use that value to encrypt the value x, and then it's going to output that onto the network. Right? And the whole point of OWL is that we're going to say that if this protocol is well typed, then this is a secure protocol in the strong cryptographic sense. All right, so how are we going to get all three of these guarantees for a functional program like this? And the main idea is we're going to look at the challenges and then address the challenges that come from doing cryptographic reductions. So if you asked a cryptographer to do this, they would take the original protocol that you started off with, and they would do a series of reduction steps. So they'd say, there's another version of this protocol that's very like the first one, but that we've changed in some way to make it simpler or more obviously secure. And they would say, we're justified in taking this step because from an adversary's perspective, they can't tell the difference between these two. Maybe because we're changing the step that affects encryption, and we assume that the adversary can't see inside the encryption. And then you would change the protocol a little bit more and a little bit more, each one justified by some cryptographic assumption. And then at the end, you're going to get some ideal protocol, where the adversary has information, theoretically no information about the secrets. And then you can hopefully trivially conclude that, of course, this is secure because the adversary has no information. All right? And so that you do that typically by saying, OK, well, the server just has the value, so it must be the right value. So that's usually the easy part. The hard part is coming up with all these hybrids. And so the way in which this would proceed at a high level in a cryptographic proof is we'd start off with this protocol, and we'd say, because we assume that we're using a secure encryption scheme, and we know the adversary doesn't have access to PSK, we can rewrite the encryption of k sub x and say, we're actually just going to write it to some location L. The client is going to magically read that location. And instead of sending the ciphertext, we're going to send a random bit string. And we justify that based on the strength of the encryption. Now we can look at this protocol and say, well, no information about k sub x. Right? It's just been magically transported to both sides. So we can do this again and just magically transport x across. Now we look at the protocol and see there's only random values being sent back and forth. So therefore, x is secure. All right. So the way in which you make these reductions work is that you have to take your actual protocol that's interacting with an adversary, and you have to rewrite it as a partial protocol that's interacting with a cryptographic game. Right? So cryptographic games are how we typically describe the security of a primitive like encryption. So there's a game describing encryption that says you can send queries and get encrypted results coming back. So we have to refactor the protocol to look like something that is interacting with this other component. And this is the hard part, right? This is the part that requires some human ingenuity when you're making a student or a cryptographer do it. And historically, existing tools have tried to either have the human write all these down in a very mechanical and tedious way, or they've tried to search through the entire space of possible reductions and try and discover it along the way. Our approach takes a very different tack to this. It's actually based on information flow types. And hopefully, if you're familiar with them, the whole idea is that you have a program that's taking secret and public inputs and producing secret and public outputs. And the rule says that you can have public inputs and secret inputs influencing the secret outputs, but you cannot have secret inputs influencing the public outputs. Right? Otherwise, you're leaking information. Another way to look at this, though, is that you take the original program and split it into two pieces. There's the piece that gets the public and the secret inputs. That's the top part, and that provides the secret output. And the bottom part only gets the low inputs and produces the low outputs. Right? And so if you can do this, then it's straightforward to prove non-interference. So let's look at this compared to our crypto reduction. Right? So if you squint at it, you can see that they both have kind of a similar goal and similar approach. You're taking one big program, splitting it into two distinct pieces, one of which has more access to information, one of which has less information. And so if you line up your information flow types properly, you can actually automatically get a crypto reduction coming out the other side. And so by proving each of those, the typing rules for the information flow type system, we can prove that there exists a factoring and a reduction step that would allow you to make this transformation of the protocol. But we don't have to search for that. We just know that once it's well typed, we have such a series of reductions, and the final protocol will be secure. So we built that into a tool called OWL that defines a tool that takes in a language looking like what you saw on the example slide and does all the type checking. And we applied it to and supports a bunch of cryptographic mechanisms. So you can do all kinds of complicated protocols. And we tried it on, I think, 14 or 15 basic protocols to make sure that it was expressive enough. All right, so this gets you to the point of saying, OK, we know that WireGuard or SSH is secure in theory, like if you could actually run the abstract protocol. But we actually, in our case, we want to run something concrete and get good performance and guarantees for that part. And so there, we're going to use our extend our OWL type checker and have a second pass that's going to compile it to Rust code. So in other words, we're going to take in our original protocol here, and we're going to run our compiler, and out will pop Rust code that looks fairly similar, but is acting over concrete objects like buffers of bytes, and has to parse those buffers of bytes, manipulate them some way, serialize them back, hopefully in a way that gets us good performance. And we're going to verify the correctness and security of this using our tool Veris for automated verification. And of course, our goal is to preserve the security of the original protocol. Right? We did all this work to prove this is computationally secure. And so we want to say that if there is an adversary against our concrete implementation, we can turn that into an adversary against the abstract cryptographic protocol. All right, so how could this go wrong? Well, one way might be if the implementation does something that the protocol on the left didn't tell it to do. Right? So maybe instead of outputting the ciphertext, we output the pre-shared key. Mistakes happen. All right, so that's obviously bad. A slightly more subtle problem would be if we do some other effect that we weren't supposed to. So in this case, we input twice instead of just inputting once. And that can either badly influence the protocol or possibly leak information about where we are in the protocol in a way that the protocol analysis didn't account for. Right? And so what we realize is that to avoid these problems, what we want to prove is that the implementation does exactly what the protocol says to do and nothing else. And that'll allow us to avoid explicitly leaking any secrets to the outside world. All right, so how are we going to do this? We need some way of teaching Veris, this first-order embedded SMT-backed theorem prover, what the protocol is supposed to do. Right? And so the way we're going to do that is by embedding this specification in a higher-order data type known as an interaction tree, or iTree. And this is a data type that has a bunch of constructors. It can return the result of a computation of type A. It can input bytes from the outside world, and then it has a function that tells you what to do with those bytes and how to continue computing with them with a new iTree. And you can also output some value and then continue computing after you output it. All right, so our client code translates into something like this. Right? So you have an input node that takes a function with the input values, does some computation on it, and then uses some of these other effects. Right, so this gives us a pure functional description of what the protocol is meant to do, and we can use this as a specification for the implementation, the actual executable Rust code we're going to do. Now, if you have a non-trivial protocol, this is kind of ugly to look at. So we actually have a Rust macro that allows you to write something that looks more or less line for line identical to what's in the original, and then expands out into the less readable but more operational iTree description. OK, so then the next question is, given the specification, how do we make sure that the implementation is doing this and nothing else? And so the observation is that we actually can have a token representing the specification. And this token is going to be treated in Verus as a ghost linear object. So it's ghost in the sense that it doesn't actually affect the execution. It doesn't show up in the compiled code. But it's linear, meaning that you can't change it in any way that the API doesn't allow. You can't forge it. You can't duplicate it. And so all you can do is evolve it along with the executable code. So the idea is that when the implementation takes an input step, we're also going to justify that based on an input node in the iTree. Right? And so the iTree says we're allowed to input, so we do an input. Internally, we might do some buffer manipulation or some functional calculations. And nothing's going to change about the token until we take some other effect, in this case, outputting to the network. And then we're going to line that back up with the iTree token. So essentially, we're going to be showing that the executable code is a refinement of the semantics of the iTree specified by the execution there. OK, so concretely, we're going to do this refinement inside of the executable code, which doesn't have to care about any crypto logic. It just has to show that it's sort of following the plan that's been specified. And so the way we do this is by making sure that the executable code can only manipulate the iTree by taking a allowed step through one of the effects. And we'll rely on the linearity of the Rust type system to automatically give us the fact that this token is unique and can't be manipulated in other ways. All right. So so how do we connect it up with the actual effects? So we axiomatize the interface to the outside world. So this is the input one. It says to read from the network, you have to pass in a mutable reference to the current token. And that token needs to be in the state of saying you're allowed to do an input at this point. If that's the case, then when we return, the token will have evolved to whatever the continuation says it should be. And based on the view, which is the abstract view of the values. So some like a sequence of bytes, abstract sequence of bytes, rather than the concrete vector that we actually return to the implementation. And then there's a similar axiomatization for output, for sampling from a random value, things like that. So basically, every time you take an effect at the executable level, you have to show that you're in the right state, and then you get back something that says, OK, now you can continue doing what we told you to. So altogether, this gives us a strategy for getting functional correctness. We take the original OWL protocol. We have a trusted spec compiler that takes the OWL specification and turns it into one of these iTrees. And if you're worried about the correctness of the compiler, you can actually stare at the two and convince yourselves that it's doing. Then we have an untrusted compiler that takes the OWL protocol and produces executable code in Rust and does a bunch of optimizations to try and make sure it'll go quickly. And then we run Verus in the background, and it tells us that the refinement checks out. The nice thing about this iTree approach, another nice thing about this iTree approach is it makes the verification very straightforward for the SMT solver. So the SMT solver is really just checking that you took each of these steps correctly. In our experience, even for very large case studies that we've done, that happens fully automatically. We aren't inserting any proof annotations whatsoever. We're just making sure the steps line up properly. All right, and of course, to make the actual protocol run, it needs to be able to parse and serialize messages. So we turn to Vest for that. And it needs to be able to do crypto. And so we turn to Evercrypt for that part. And it's all nicely automated so that the developer isn't having to get in and mess with this machine-generated code. All right, what's the next challenge? So we have to worry about side channels. Right? So a place where you might read secret information and then make different decisions based on what you see. So this is a obviously toy example, but if you look at the secret and then take too long calculating something, then that's clearly a problem. Now, this is something people have looked at for many years. And if you're writing a crypto library, the tool you often turn to is something called type abstraction. And so you define a type like secret buffer. And in Rust terminology, we have a public name for that type. And internally, it keeps track of a regular buffer. But this is not exposed to the rest of the code. So if you're not in the secret buff module, you can't see those bytes. You can only interact with them through this interface. And this interface is designed to be constant time. Right? So the length of the buffer is public. You can create a new subrange of the buffer, and that's not leaking anything. You can sort of cast a public buffer into a secret buffer, and you can put two together, which gives you something that's longer, but you already know the links to start with, so this also isn't leaking anything. So if you're working on something like RSA, this is enough, right? Because in RSA, you don't actually, you're going to keep something that's secret, like the key, it's just going to stay secret the whole time. However, in a protocol, it gets trickier. So in our, even in our simple protocol, we have this step here, where we had a decryption operation. So decryption takes in your secret key, and so the output ought to be secret, if you just look at information flow. And yet, we need to make a decision here as to, did the decryption succeed? Right? That's what this match statement is doing. Now, intuitively, this should be OK, because if you have, so cryptographically speaking, if you have a secure encryption scheme, then the adversary already knows a priori that if they pass along a valid ciphertext from the sender to the recipient, then decryption will succeed. And if the adversary changes that ciphertext in any way or creates a new ciphertext, then it knows it's going to fail. So leaking this information to the adversary is perfectly OK, because you're not telling them anything they don't know. And that's justified by the cryptographic assumption we make about the encryption, and is encoded in the typing rule for OWL. But somehow we have to convey that information to our implementation to say when we're allowed to declassify a secret buffer, and do so in a way that doesn't leak information. Right? Historically, declassification has been one of those super dangerous things. You say, well, we have to put it in there, and then just hope the implementation doesn't misuse it. So our solution to that is to do semantic declassification. Right? So we're going to take the information that the OWL has already computed in a very rich and complex way, and we're going to collapse this complicated lattice into just definitely public and maybe secret. And then we're going to extend our I tree with one more node that allows declassification. So we have our original I tree here. We're going to add a declassify node. And that declassify node will say, you're allowed to perform one declassification operation at this point. And so that operation might be a control flow operation, like the match. It might be a cryptographic primitive, like decryption, that we know might fail. Anything that's been checked by OWL that we can then hand off to the implementation. And the important thing, and as a small optimization, instead of telling you what you can declassify right at this moment, we actually give you a separate token that says, when you feel like it, you can declassify the result of this operation. And that's because by default, the I tree enforces a very sequential control flow, which is desirable when it comes to network effects. But for performance, oftentimes you want to fuse different operations. You want to say, I'm going to decrypt, serialize, and write it to a buffer all in one. And so we want to be able to decouple that from the actual moment when we decide to do the declassification. So that turns out to be a small but important optimization along the way. So to apply this, we've applied it to a bunch of protocols, the largest of which is WireGuard. So WireGuard is a VPN protocol for establishing a secure channel to a corporate office between two corporate offices. It's used in the Linux kernel. It's very popular for creating these tunnels. So we first verified WireGuard in OWL. So we wrote a bunch of types on it, and that gave us a bunch of cryptographic properties for the protocol itself. And we did it without too many lines of code, or too much proof effort, and then automatically type checked it, and then extracted the core cryptographic routines, things like the handshake and the transport, which are actually doing the cryptographic parts. And then we integrated it into WireGuard Go, which is the state-of-the-art implementation. And we also integrated it into WireGuard RS, which is a Rust-based implementation. And it's important that you sort of take plan for this, because otherwise, these implementations do a lot of other stuff beyond the crypto. So they do things like network packet reassembly. They do something like multiplexing, stuff coming off the wire. They remember a bunch of state about the IP address of the client. And in theory, you could verify that, but that's not really the focus of the cryptographic verification. One other nice bit about the ones that are implemented in Rust, you can actually use the Rust type system to make sure that when we hand off things like the keys that are in the state, that the other Rust code, even if it's unverified, doesn't mess with the keys. Right? You can use, Rust has fairly good type encapsulation, so you can use that to say, here's some opaque struct, please give it back to me when you want to call back into the library. All right, so this is our main performance graph. There's lots more in the paper. This is looking at the throughput that you get from these different implementations on the left, And on the x-axis, we have the line delay. So how much latency is there between the sender and the receiver. The green line is the Linux kernel implementation, which is the one that most people in the world use. The yellow is the unmodified WireGuard Go. So that's state-of-the-art performance. And then the blue and the red are the time running with OWL, and two different versions of OWL. And you can see that once we move, at the very beginning, there's a little bit of a gap between the two. At the fairly unrealistic half a millisecond layer, once you get past, say, a millisecond and a half latency between the two parties, they become indistinguishable. And a grad student discovered that the latency between two data centers in the same failure zone in Amazon is multiple milliseconds. So we think that for any realistic regime, we're looking at more or less identical performance, even though you're using fully verified cryptographic implementations. You might say, why is this? The intuition is that if you're doing a good job at your protocol, then the only thing it should be doing is sort of shuffling around data in an intelligent way and handing it off to the crypto. So a good protocol implementation should be spending 90+% of its time in the crypto. And so if you're using a state-of-the-art crypto library like Evercrypt, then you should be getting good performance naturally. Sadly, that wasn't always the case. There have been verified protocol implementations that copied data all over the place and did a lot of allocation. And it is possible to pay for that if you're not careful. But with enough optimization, you can get these things to line up quite nicely. So just to wrap up this compilation part, right, so we're using the I trees as a formal specification, along with these linear types to enforce the fact that the implementation is following and doing exactly what the implementation or the specification says and nothing else. We're able to get state-of-the-art performance, outperforming the Linux kernel implementation, even though we're running in user space. And that's the result of lots of clever engineering on the part of the people that wrote WireGuard Go and from my hardworking grad students. So since this is the secure compilation workshop, I want to point out that I've been carefully saying security-preserving compilation, not secure compilation. So what would you want to have to do if you wanted to get an actual end-to-end guarantee? One, I think you'd have to port OWL from its current Haskell-based code base into Rust or Varus so that you could actually do the formal guarantees on that side. Then we need some mechanized semantics for Rust and Varus and the guarantees that Varus gives you on top of that. And then we just need secure compilation for all of Rust. So looking at this list, I think we could probably pull off one. There's a lot of hard work going on mechanizing semantics for Rust. And so we might imagine that would emerge eventually. This last one seems daunting. But there's lots of bright, eager PhD students here. And so if you want to go for it, please be my guest. And let us know when you get there. So before I wrap up, I just want to mention that this work was in collaboration with lots of great people. The ones shown in red were all students or members of my group at one time, or in some cases still are. The ones shown in bold are people who were leading one or more of the components here. And I'd particularly like to call out Josh Gancher, who was a postdoc in my group and now is a professor at Northeastern, who is the brains behind a lot of these projects and also some of these slides that I'm using. So just to wrap up, we are in the process of building towards formally verified end-to-end protocols. We've been focusing hard on coming up with ones that are practical and can meet some of the challenges like lacks of proper specifications or the need for good performance that we see in the real world. And one of the key tools we've been using is this Varus tool that enables us to get good performance and strong guarantees coming out the other side. So thank you.
Thanks a lot for the very nice talk. If there's any questions from the crowd, we should have a working mic at some point. Otherwise.
Hello. All right. Thank you for the great talk. Actually learned a lot of new things. So to prove the refinement between our specification and the Rust code, you embed the I3s as a Rust trait and show the unverified using Varus. So an alternative approach, I believe, by David Bazin and Peter Muller's tool, and their students, where they refine Tamarin implementation to Go, Python, and Java uses separation logic specifications and I/O specifications in the style of Petrinets. Could you elaborate on the advantages or disadvantages of using iTrace compared to that?
Let's see. So I guess one difference is that we were starting from OWL, which gives you a different set of guarantees and a different format for your starting definition. Looking at the Tamarind work, it looked like they had to do non-trivial work just to sort of recover the parties and the state. So we had some advantage just starting from OWL. I think the main advantage we found with the iTrees is that it makes the SMT-based verification go very, very smoothly, because you're not proving any complicated steps. You're just saying these are moving in fairly similar steps and doing fairly similar operations. And so we've been pleasantly surprised at how easily the SMT solver discharges all that. Mm-hmm. And I think that's partly because we're regularly synchronizing, right? We're saying we're doing some computation, then we do an I/O. And at that point, you prove the last 4 or 5 things were right, and you're good to go. And now you've moved to a new state where you're doing some more, and then proving that those next couple steps went well.
So in terms of expressivity, you didn't really find any shortcomings?
Well, I think we didn't in our examples. One limitation is because we use inductive data types in Veris, we can't easily express while loops. In our case, we can get away with that because cryptographic protocols are typically set up as event handlers, right? So you call in, you do a finite number of things, and then you come back. If you wanted to do something loopy on the inside, then we'd have to work harder on that.
Thank you.
Sure.
I had a question here. Yeah, thanks for the very cool talk. I have actually multiple questions, but like one, let me start with this. In the initial slide, you showed Veris, C3, and Lean, but you didn't, like Lean didn't appear later in the talk again. Could you maybe briefly say where does Lean fit into this?
Yeah, so that's because it's more of an aspirational goal. So we have a very, very narrow pipeline that, just in the last few months, that lets you take certain Veris obligations and export them to Lean. And we're still trying to figure out how far we're going to take that. The idea is that for certain kinds of proofs that the SMT solvers are not adept at, it might be nice to kick some of those over to the Lean side. So we're collaborating with Jeremy Avogad on the Lean side, and I think he imagines that eventually we'll wind up with most of it happening in Lean. I imagine we'll end up with little bits happening in Lean, and we'll try it and we'll find out where we wind up.
Yeah, thanks.
A quick question. The refinement that you prove in Veris, is that a termination preserving refinement, or is it?
Yes, in the sense that the post condition of each of the methods says that you must be in a ret state, and the value that you're actually returning matches that ret.
Okay.
Quick question. Can you elaborate on the control flow declassification that you mentioned? What exactly are you declassifying there?
So when you do a decryption, we allow you to classify whether or not it succeeded. Not the contents, but whether or not it succeeded, which then allows you to do a control flow based on that, for example.
So I mean, you could put like a match operator in that I-tree declassify.
Yeah, so we have declassifiers for decryption, for whether decryption succeeded. We also have other ones for control flow because OWL won't let you make control flow decisions on secret data.
Okay. Thank you.
Thank you. I was wondering about the connection between the type system you mentioned, the information flow, and then the kind of equivalence that you talked about for that they're using in the computational model in the crypto world, right? So could you elaborate a little bit more on what is it that precisely you prove for this type system, and how does it connect to the notion of equivalence, and what is it sort of a bit more precisely?
Yeah, so at a high level, the type safety theorem for the language says that if it's type safe, if it's well typed, then there exists a series of cryptographic reductions between the protocol and an ideal one where all of the secrets are properly preserved and integrity is preserved. The way in which that actually happens is that so the typing rule for encryption, for example, says that the proof for the encryption rule says, well, we can always find a top-level key, like the key that nobody else encrypts. And so we can do a reduction step, but where we factor the proof into the part where you're interacting with that key through the sort of standard interface for encryption and the rest of the protocol. Then we can do a reduction based on the encryption game that says, okay, if this key is only being used for encryption and decryption, then we can invoke the in CPA assumption that says, okay, we can replace that use of the key with just magic values. And so that step happens generically in that proof. And then the proof says, okay, well, once we've done that, then we can look for another key. There must be some other key that's at the top of the hierarchy. And we can do that over and over again until we've eliminated all the cryptographic keys from the protocol. And then the rule for signatures has something similar, but more on the integrity side.
Does that mean you avoid having to reason about probabilistic adversaries?
The reasoning about probabilistic adversaries happens only in the type safety proof, not in the type checker, which is I think one of the advantages of it. At that point, we're just doing pure type checking.
Yep. So, at some point, you were talking about like a real protocol implementation that gets refined to an ideal specification, and the lingo you're using and the setup you're describing to me speaks of universal composability, but you haven't mentioned universal composability. Why?
UC is beautiful but hard to work with. And you can talk to, actually, Josh has papers on both sides, so he can tell you about the positives and negatives, but UC is unpleasant to work for and so doesn't have good abstractions for some things like signatures, for example. It's typically operating at a higher level, like MPC protocols.
So, this whole setup does not yield universally composable protocols.
That's right. So we're effectively doing a composable proof, one-shot proof for the entire thing in a modular way.
Okay.
Thank you for the talk. At some point, you mentioned that one key optimization is about like rearranging where the classification happens.
Mm-hmm.
Aren't you worried that if you say declassify too early, you might end up leaking some secret?
It's a good question, but no, because the I-tree will say, at this point, it's OK to declassify, but if you decide to declassify later, that's fine too. And the effects of that will only be visible when you do one of these effects, and the effect system won't let you output something like too early or the wrong value.
Got it. So does that mean also that you're like safe from Spectre attacks?
Ooh, I don't think I want to claim that.
We can turn off the record.
I think if we are safe from them, it's inadvertently. So I think we'd have to spend a lot more time to say something definitive about it.
By the way, are your crypto verified implementation also safe, secure against Spectre, or just sequential CT?
Again, the crypto implementations and the parsers are proven secure against sort of basic side channels, timing and memory. None of it's Spectre secure, except if we got lucky.
Great, thank you.
Sure.
Yeah, so it's also about the declassification part. You say you so you add to the I-trees declassification. Do you have? I mean, you said it's semantic, right? You have some notion in the compilation from old to the I-tree that justifies the declassification at every point from the computational side. Yes.
That's right.
Okay.
Yeah.
So it's completely automatic. You don't even have to formalize it manually.
Exactly.
Okay.
Did we have another question here?
So it seems that one of the points is that you build this type system that allows you to claim that type safety implies the correctness and all your property.
Mm-hmm.
And one question I was wondering is how much that offloads the complexity of the verification into complicated types that you have to think through, or whether in real life the types are relatively simple, and how much debugging you have to do to get them right.
Yeah, so you do have to put some thought into the type system, particularly for something complicated like WireGuard. These simple ones, it's fairly straightforward to write down the types. WireGuard is definitely more involved. And I know Josh has put a lot of effort into making the error message is more useful, and we'll try and tell you, like, you might try this because. But there are definitely cases where it falls back to, here's the type context, figure it out.
Yeah.
But I think that's just a sign of it's a relatively young tool, and there's room to improve there. I think Josh is also leading an effort at Northeastern to try and refactor OWL to make it easier to extend with new primitives. Right now, doing that requires doing a bunch of Haskell hacking and writing out a paper proof that you got it right. And the hope is that we can instead have a small kernel that says, here's what you need to prove about your cryptographic primitive to sort of fit into the type system. And that would give us more confidence that we got that side right.
So one of the reasons that there's not been that much work in the intersection of protocol verification and computational security is that it's not always entirely obvious how to define the network model.
Okay.
So what model of a network are you using?
So in this case, it's
sorry, maybe just so the reason being that you're combining probabilistic encryption with a priori non-deterministic network, so there's some subtlety in that.
Yeah, so our network, I think, is formalized as, like, the adversary is literally the network. So the adversary gets to sit there and say, I want protocol participant 1 to run operation 2 or operation A, and then I'm going to take something from that, and then I will choose to invoke protocol participant 3 on operation B and pass it some information. And so it's entirely up to the adversary how it decides to schedule the messages, what messages it decides to deliver. And so we don't guarantee anything about liveness. We just say that if you get a message and it successfully decrypts, then it has the value you're expecting, and the secrets remain secret.
Okay, so and you're assuming that the adversary is just another program, right?
Yeah, essentially.
Yeah, right. Cool. Thanks.
Sure.
Yeah, thanks. So yeah, I think this whole picture that you've shown here is like really cool, that you have all these different parts and like how they fit together. I'm wondering, what are is there actually anything still left, or like what are the next steps to do there? Like, can this picture evolve in like other ways?
Yeah, I'm going to retire after this, actually. No, so I used TLS as a motivating example, but you notice that we didn't have any graphs for TLS yet. So we're still at the point of trying to scale up OWL to tackle TLS. I think there's there's some just engineering work needs to go in there, some making it easier to use, and I think there may be some trickiness to the way in which TLS behaves and the sort of recursive nature of some of the sessions that we'll have to address on the more theory side. I think making OWL more modular and easier to extend is still a big thing. Like, if you want to use the cryptographic primitives we already have, great. If you want to add your own, it's non-trivial. What else? I think there's plenty of work to be done above this layer. Right? So once upon a time when we had the Everest project, we wanted to go all the way up to HTTPS. And HTTPS naively is just basic HTTP over TLS. But there's actually a lot of complexity when it gets to like same origin policy and cookies and how cookies are pinned to different origins. And you can imagine getting to that point, which I always thought was interesting because it seems like these days everybody wants to put an HTTPS server on their IoT device, which as a security person I find terrifying. So it'd be nice to get to the point where you can say, okay, here, if you want to put a server, put this one, and then make all of our IoT devices more secure. So those are a couple of directions we're looking at.
Yes.
Do we have any final question? If not, just actually one curiosity. All of the performance graphs you were talking about were always good. Why? Is it just execute like going through Rust? Is it like, was that like the Rust executable that makes it that makes the performance go well, opposed to other alternatives? Or
so going through Rust certainly helps, but it's definitely not enough. And I can tell you that because the very first version of the OWL compiler that we had that went to verified Rust, we got it working maybe 3 days before the deadline. We ran some performance numbers, and they weren't great. And so we did not submit to the deadline. Instead, we went in and my student learned all the nuances about how costly it can be to allocate memory and how costly it can be to copy memory. And then we did a bunch of looking at, okay, how can we automatically figure out, say, this buffer is never going to be used again, and then so we can recycle it and do everything in place rather than doing a bunch of copies. How can we use the right data structures to avoid, to pass around references to stuff instead of copying it as we go. So some of it's going the extra mile to match the optimizations that the regular code is doing and making sure your proofs still go through. So like that's where the declassify op came from. We had this clever optimization based on fusing stuff. We started working on the declassification and realized, oh crap, that's going to break this. So then we need to do one more layer of indirection.
Cool. Well, thanks again. Give it up for Bryan for a very excellent keynote.